All right, we're starting.
Hopefully you remember your optimization handouts. We're going to continue with optimization. So, I think we only did one example from this sheet so far. The first one. I think was a good example to segue into this topic. Anyway, so optimization, remember the whole point is we want to optimize the situation, making it better within certain resources whenever we can define better in terms of making something maximum or minimum within some restriction, right? So we have a bunch of steps for that. We know how to use calculus to find absolute maximums and minimums. So that's sort of the idea. Again, these are the steps. Always do these steps in this order. Basically, that's that. So we're just going to jump into the next example. Example 2 from the handout. So now, first step is to what?
Read.
Read. Read the problem very carefully. Make sure you understand what it's saying. Okay, so let's read that. Design an open rectangular box with square ends on the left and right side, having a volume of 36 cubic inches that minimizes the amount of materials required for construction. Okay, so that's the equation. And this was actually a past final exam problem. So this was on the spring 2010 final. So it's a bona fide question. Okay, so second step was to do what? Draw a picture. So here, they talk about a box. So we're going to draw a box. How are we going to label it? How do you label this box?
Using X and Y.
Sure. How? Tell me how to label it.
The 4 sides.
What's this side?
X.
This length here. Okay, X. This?
Y.
This?
X. Oh, Y, yeah, Y.
Why would that be Y?
Because you have X on the floor.
Okay, so Y. Why would that be Y? Okay, so they said the left and the right side would be squared. Was it an open box? It's open, right? So there's no top, right? But we know that the left and the right side are squares, which means if this is a Y, that also has to be a Y, right? That's an important thing, right? So that's why we read the problem, right? To know that these two are actually the same variable. It would be very difficult to get anywhere without knowing that. Okay, so that was step 2. Step 3 was to what?
Come up with an equation.
Come up with an equation. How many equations do we need?
1.
Remember, that's the main difference between, one of the main differences between optimization and related rates. In optimization, we need to come up with 2 equations. One is called the objective equation, which describes what you want to maximize or minimize. The other is called the constraint equation, which describes the restriction you have in order, in the context you're given. Okay, so what's our objective here? What do we want to minimize? Surface area. Right? It says minimize the amount of material used. Well, if we're having a figure that's made up of 5 flat sides, the area is how we're going to be measuring how much material we're going to use. So how do we get that function? Just take the area of all the sides and add them together. So what are they? So here, what's the area of this? X times y, which is going to be the same as that. This is x and y. This is for the front and back. Plus y squared plus another y squared. Right, so there are 2 of these for the front and back. 2y squared. And this is the left and right side. Plus xy, which is the bottom. Now notice, again, because we read the problem very carefully, we know that the top is open, so there is nothing to add for the top. Okay? So, in other words, our objective equation becomes A equals, what, 3xy plus 2y squared. Okay, so that's going to be our objective equation. Right? We want to minimize A. Right? We want to minimize the amount of material used. Okay, what's our constraint? What's the restriction here? Okay, so remember the constraint is often the guy that they actually give you a value for. Here they told us the volume was 36, which means that's what the volume has to be. That's a restriction. That's a constraint. So we know that the volume must be 36. But based on this diagram, how do we find the volume? What is it? xy squared equals 36. Right? This is basically length times width times height. Right? So I take x times y, that's going to be my volume, and it must be 36. That's a constraint. What was step 4? You are going to solve for one variable in your constraint. You're going to plug it into the objective. What do you want to solve for? So we know that xy squared equals 36, which means that my x is equal to 36 over y squared. I'd rather solve for x here because, you know, y you get radicals and stuff and you have to worry about pluses or minus. Well, it's a length. We don't have to worry about the minus part, but I'd rather avoid radicals, so I'd solve for the x instead of the y. And so now what I'm going to do is I'm going to plug that into the objective. So whenever I see an x in the objective, I will plug in this expression. So I'm going to have 36 over y squared times y. 2y squared. This cancels that. What's 3 times 36? 108. Okay. That was step 4. What is step 5? Right, now you actually want to find where it's going to be a maximum or a minimum. In this case, we want it to be a minimum. So we're going to find the critical points and test them, which one gives us what we want. So here we have A prime equals, what's the root of this?
Y squared. Over y squared. Plus 4y.
Right. Now for minimum, we set A prime equals 0. This means I have minus 108 over y squared plus 4y equals 0. How do I solve that?
So for y?
Common denominator, or it's an equation, so we can actually just clear the denominators. Multiply both sides by y squared. And I will get minus 108 plus 4y cubed equals 0. In which case I have y cubed is equal to 108 divided by 4. Does that go into it exactly? 4 into 10 goes 2 times, remainder 2. 4 into 28 goes how many times? 4 into 28?
7.
Goes 7 times, so that's 27. And now we have y is equal to the cube root of 27, which is 3. Now we are at step 6. What did we do at step 6? Answer the problem. Answer specifically what they're asking you for. What do they ask us to do? Well, design a box. How do we tell them how to design a box? Well, we'll tell them the dimensions. So I'm simply going to tell them what to make the length, what to make the width. So I already know one of them. Y is equal to 3. So what about the x? x is equal to 36 over y squared, which is 36 over 9. It's 36 over y squared. Okay. That goes 4. And so we want the box should be, there are tons of ways you can write it. Something like 4 by 3 by 3. Or you could say, you know, width is 4, length is 3, height is 3 or something like that. That is the answer to the problem. Questions? Okay, let's move on. 3. A rectangular corral of 162 square meters is to be fenced off and then divided by a fence into 2 sections, as shown in the figure to the right. Find the dimensions of the corral so that the amount of fencing is minimized. Okay. Again, this is actually another final problem. And here they gave you the diagram. I'm not going to give you a diagram, but whatever. They gave you a diagram. 1, read. 2, come up with a picture. They actually gave us the picture. However, they didn't label it for us, so let's actually label it. How do you want to label this? How do you label it?
The total of 162. For
What
the
does that
leg.
mean?
So the longer ends would be this, and then the says.
So you're going to call this
It will be the
x,
same, but it could be the same.
this is y.
Then there will
Okay.
be y as well.
Right, so this is a rectangle, so that will also be y, that will also be y, and this will also be x. Okay, so we're going to label it like that. Okay, so that was step 2. Label. 3. What is the third step? The 2 equations. So what's my objective? What's my constraint? What do we want to do here? Minimize what? Find the dimensions so that the amount of fencing is minimized. What's the amount of fencing?
That's a perimeter.
It's a perimeter, the distance all around, the length of all of these lines. So what do I want? Well, I'm going to call it P for perimeter, and that's going to be what here? 2x plus 3y. Right? I want to minimize that guy. What's my constraint?
162 square meters.
What does that mean?
That's the perimeter.
That's an area. Right? One, it couldn't be the perimeter because I know the perimeter is what I'm looking for, so it can't be that. What also tells you it's an area is because they told you square units. Right? Remember, length is just a unit. An area is a square unit. The unit squared, feet squared, or yards squared, or something like that. And the volume is a cubic unit. So they'll tell you feet cubed, meters cubed, cubic meters, something like that. So we know its area is that guy. And so what is the equation here? X times y is 162. So here I'm given the constraint of what the area must enclose, and I want to minimize the perimeter. Okay. Step 4. Solve for one variable from here, plug into there. It really doesn't matter who, usually. So what do you want to do?
Divide by y.
Okay. So here you solve for x, 162 over y. Again, it doesn't really matter who you solve for, just who's easier. I probably prefer to solve for the x because I'd have to multiply it by 2 instead of multiply it by 3. just some arbitrary reason, but that's fine. And so what I do is I'm going to take that, I'm going to plug it into the objective. So now my P becomes 2 times X. So it becomes, what's 2 times 162? Okay. Which brings us to step 5. What are we going to do? Derivative, which is this guy. And so now I know I want to minimize, so for minimum P prime equals 0, this means minus 3 to 4. How do I solve that?
Multiply by y squared.
Take care of the denominators by multiplying by the LCD both sides. I get minus 324 plus 3y squared equals 0. And so now this means my y squared is equal to 324 over 3. Does that divide evenly? What is it? 108. You know something is divisible by 3 if the sum of the numbers is divisible by 3. 3 plus 2 is 6. 3 plus 2 is 5, plus 4 is 9, so that's divisible by 3. I try to divide it anyway and hope for the best. And so, what? Come again? And so now my y is going to be what? Square root of 108. Obviously, I'm not going to take the negative, just ignore it because we're talking about length here. So square root of 108 is what? 9? What's square root of 108?
I don't think that works.
Can we divide 108 by anything? It's divisible by 3. No, not necessary. We'll leave the exact answer, so we'll leave radicals in our answer. So 3 goes into 108 how many times? 36, right? So we have 6 radical 3.
What about if we leave the answer as y equals radical square root of 108?
Yeah, probably
Will that work?
That's fine.
That's a no. Okay, thank you.
Okay, so what else are we supposed to be finding here? Find the dimensions. The dimensions is what we're after.
That's a plot
Okay,
y.
so that's 6. We need the dimensions. So I already know the vertical dimension. Now I need to find the horizontal. So x would be 162 over y. So that's going to be 162 over 6 radical 3. Does 6 go into that? Well, I know 3 goes into it. But does 6? Six into 16 goes 2 times remainder 4. Does 6 go into 42? Huh?
I think so.
Yeah, it does. 36, 42.
Okay.
So 27.
27 radical 3. So now the dimensions is just going to be.
Okay.
This implies vertical dimension equals 6 radical 3.
Is that why?
meters. Yes, according to our original diagram, we call this y and that x. And the horizontal dimension is 7/3 meters. Let's do another one. See, we're going to go through these same steps all the time. Example 4. Step 1, read the problem. A cylindrical can without a top is to be made to hold 8,000 pi cubic meters of liquid. Find the dimensions of the can, which will minimize the amount of materials needed to make the can. That is, minimize the surface area of the can. If I was writing that problem, I would tell you it was surface area. So hopefully you would have read that and recognized that surface area is something that's of concern. So step 2, they actually told us it was a can. So. Okay. How would we label this? What are the important dimensions here?
Radius.
Radius is one thing we're going to want to know, so I'm going to call that here R. And the height is also something H. So that's going to be our diagram. 3. We're going to have the objective and the constraint. What is our objective here? I'll probably need more space in the direction. How do we figure out the objective? We want to minimize. Okay, tell me what the surface area is. The cylinder can without a top. So notice that there's no top here. That's going to be important. How do we figure that out? So rectangle in a circle, right? The trick is, you kind of cut along one side and then you unfold it, right? So there are 2 sections here. There's the bottom, which is a circle, plus there's a rectangle, where 1 is the height and what's the distance here? That's the distance that goes around the top of the can, which is going to be circumference, which is 2 pi r. Okay, and so my area, the surface area, is going to be the area of this plus the area of that. Right? So that's the bottom and the side. There's no top, but the area of this would be pi r squared. The area of this, length times width. So that's going to be my objective equation. What's the constraint here?
8,000 pi. That's the area.
Volume?
Volume, right? So they told us the volume is 8,000 pi. I know it's volume because they mentioned cubic units, right? So they told me that the volume is 8,000 pi cubic units. So because it's cubic units, I know it's volume. What's the volume of a can? Pi r squared h. Right? The volume of any uniform figure is the area of the base times the height. Okay, so that must be 8,000 pi. Which brings us to step 4. Step 4 is to solve one variable here, plug into the other one. Who do you want to solve for? I'd solve for h to avoid having to take the square root. So this is going to be 8,000 pi divided by pi r squared. Pi's is cancelled. that just h equals 8,000 over r squared, which means I'm going to take this and plug it into that. Everywhere I see an h, I'm going to write that, guys, so this becomes pi r squared plus 2 pi r times h. This r cancels with that. That's 16,000 pi r. Step 5. Find the derivative. Derivative of this. Derivative of this. What's the derivative of that part?
1.
No.
R squared.
Right, that is r to the minus 1 to the power rule. Okay, so now we want to minimize the area, correct? We set a prime equal to 0. So we have 2 pi r minus 16.3 pi over r squared equals 0. Multiply both sides by r squared. I get 2 pi r cubed minus 16,000 pi equals 0. Divide both sides by pi. Divide both sides by 2. I would have r cubed is equal to 8,000, which means that r is equal to 2. R is equal to 20. 20 times 20 times 20 is equal to 8,000. So now we move on to step 6. Find the dimensions which will minimize the amount of surface area. So I already know what the radius is. I need to know what the height is. Again, what's important here is dimensions. My r is 20 squared. It's 8,000 or 400. Radius is time the height is 20. Questions? One more example here, the department store example. Is there questions? The manager of a department store wants to build a 600-foot rectangular enclosure in the store's parking lot to display some equipment. 3 sides of the enclosure will be built from redwood fencing that costs $14 per running foot. The 4th side will be built of cement blocks costing $28 per running foot. Find the dimensions that will minimize the cost of the building materials. This is from the spring 2009 final. Let's start over here. Step 1, read. Step 2, diagram. So what do we have here? It's a rectangle. So let's label it length, width. Right? It asks us to find the dimensions. Right, so the dimensions we don't know, so the length and width I actually don't know. But I know it's a rectangle. What else do I know? 3 sides is redwood. 1 side is cement. So let's make sure I identify the cement side. Let's say this is the cement side. All the other 3 sides are redwood. Okay, so that's my picture. Okay, so tell me my equations now. So I need an objective, I need a constraint. What's my objective? Remember how to figure out your objective, you figure out what you want to maximize or minimize? No. What do you want to minimize? You want to minimize cost, which means our objective function is going to be a cost function. How do I find the cost function for this guy? So it says 3 sides have redwood, which costs $14 per running foot. So each of these guys costs $14 per running foot. And then cement blocks cost $28 per running foot. So what's the cost of this fence here? What would be the cost of this side? 14y. Because of this side? 14y on that side? 14x on this side? 28x. That's it. So basically this is going to be 14y plus 14y plus 14x plus 28x. This is for the cost for the left, the right, bottom, the top, according to that diagram. So C is equal to 28y plus, what do we have here? 14 plus 28 gives me. That's my objective function, the cost. And so they want us to minimize cost. Cost is objective. What about constraint? Well, it's what they gave us. So it says here, it's a 600-foot rectangular enclosure, right? Which means that the perimeter around is 600 feet, right? So this length plus that length plus that length plus that length is 600. So I know that 2x plus 2y equals 600.
Do you get the 2x and 2y from the sides?
Yes, I'm adding the perimeter. So it's x and y. And
Okay.
y. So the total distance around is 600. So now that brings us to step 4. I'm going to solve for one variable here, plug it into the other one. So 2x plus 2y equals 600. Or in other words, x plus y equals 300. Who do you want to solve for? No, almost doesn't matter. But I guess I'd rather multiply by 28 than I would by 42.
Yeah.
So, well, it doesn't make much of a difference. I'd solve for y. So now my cost becomes 28 times 300 minus x plus 42x. there is a mistake in this problem.
How do we know if
I hope the spring 2009 finals, the spring 2009 kids didn't. You can find C prime here. C prime would not be 0. C prime would be 28. No. C prime would be 42 minus 28, which is never 0. Yeah, so there was a typo in this final. Let's see, can we salvage it? I think maybe if we thought of the 600 as area, we could probably fix it. So yeah, the constraint doesn't work. There's a typo in that final. Maybe that would make it better. We've got something to work with. So let's note. No guarantee that the numbers are going to be nice now, but it definitely won't work by telling me the derivative. Assume 600 feet. Feet squared area. So you have x times y is 600. So in step 4, we have, and I price off the y equals 600 over x. This means C would be 28 times 600 over x plus 42x. This means probably like that. Brings us to step 5. We're going to find the derivative. Want to minimize the cost, so for min, set C prime equals 0. So this has a nice solution. 600 over x plus 42 equals 0. That divide evenly, 40 times that. Huh? Said 400. How do you know that?
Calculator.
We're not allowed to use calculators. You guys better remember your arithmetic. Come again?
Simplify 20 to 42.
Oh, you divide by 2 first? Sure. You could even go higher. You could divide by 3. But sure, you divide by 2. Here you get 21. Divide that by 2, you get 14. You divide by 3 here. You get 7. Divide by 3 there, you get what? 200. Divide by 7. You get 2. You get 400. There are tons of ways you could have
Oh
done
my
that.
god, that's a lot.
And so, what do we want to do? Minimize dimensions, right? Find the dimensions, right? Find the dimensions. Okay. So that was step 5, so now we're on to step 6 to answer the problem. We want the dimensions. So I know x is this, so my y is 600 over x is 600 over 400. This means this equals 400. Say 400 by 3 halves rectangle. Cement side is, my cement side was the x side. Hold on. Questions?
Isn't the cement more expensive? Shouldn't it be the smaller number?
Yeah, but there's one of the redwood sides is also 400. For example, I had to change this problem. I don't know if that actually makes the specific numbers make sense, because how they had it before just didn't work. It's also already strange that one side is 1.5 feet. But whatever, I just took it off the top of my head to try to get something at least a little bit meaningful. Yeah. The other two you try on your own. That was really quick. That's optimization. Let's move on to more optimization. So there are 2 sections on optimization in your textbook. We just finished the first one. I think this was 4.6. This one covers what you're going to learn in 4.7. So again, the same steps apply here. The only difference is they sort of figured out the formula for you, and you kind of just always just use this formula. So you don't have to draw a diagram or anything because they tell you the formula. I think there are other applications in this chapter, but we only care about this particular one, inventory cost. So again, the handout kind of tells you everything you need to know. So what we want to do here is minimize inventory costs. So if you pretend you're a business owner and you're selling a certain product or products, right? You have costs associated with storing your inventory and stocking and restocking your inventory. Every time you make an order, you have to pay, right? You have to pay delivery fees, you have to pay labor fees, you have to pay for the things you actually ordered. And to store the stuff, you also have to pay stuff, right? You have to pay rent for the space that you're storing them in, etc. So pay the salary of someone who's watching the stuff so that no one steals it, right? So all of these things cost something. And so the inventory cost application is just going to try to figure out how can you minimize this cost, meaning how many times should you order inventory, how often that can make the difference here. And so what happens is, let's say over the course of a year, right? You know you usually sell 1,000 products. Does it make sense to order all 1,000 products up front? Or does it make sense to order 2 shipments of 500 each, you know, halfway through the year? You order 500 in the beginning or 500 in the middle, or maybe 4 shipments of 250, right? All of these would have different things that you would have to consider. First of all, if you order 1,000, you need a lot of space to store all that stuff, so storage costs are going to go up, right? But then if you order 2 sets of 500, then you're going to have to pay 2 sets of delivery charges instead of 1, right? There are a lot of things to consider. What's actually the best allocation, right? That is what inventory cost is going to try to answer, right? So, of course, you make some simplifying assumptions here. We're assuming that you are selling a steady amount of products throughout the year, right? So like every month there's a certain predictable amount that you will sell, right? And which means the number of products in storage at any given time will follow a graph that looks like this, right? So basically X is the amount you order. Eventually that runs out, and then you order X more, and eventually that runs out, then you order X more, then eventually that runs out, you order X more. The average will be the halfway mark. At any given time, you're half done with the products, right? At some point, you start to order more as they are running out, and your graph will end up looking like this, right? So the average storage capacity that you need is X over 2 by this assumption. So kind of a simplifying assumption, but in real life, you might make more complicated assumptions. But for this kind of problem, we're going to make these simple assumptions. You're selling at a steady pace throughout the year, right? And so you end up with a graph like this. And therefore, you end up with this equation. C of X equals order cost times total number of items over X plus inventory cost times X over 2. Now the idea behind this is the cost to place each order. This is under the assumption, assuming X units are ordered each time. Right? So this is what you're going to pay each time you make an order. This actually gives you the number of orders you make, right? So for example, if you know that you sell 1,000 items per year and you want to order 200 items each time, then the number of orders you're going to make is 1,000 divided by 200, which is you're going to make 5 orders throughout the year, right? So this tells you the total number of orders, right? And this product actually gives you the ordering cost, right? This is the cost for you to order stuff. That's one part of the inventory cost equation. Then inventory cost here basically means storage cost. How much you're paying to store this thing, right? So in rent, in salaries for security guards, and all that stuff, that goes into your inventory cost. It's like how much you're paying to store. Now we know that because things are running out while you're selling them and you're reordering, the average amount that you have in storage at any given time is going to be X over 2. So then this actually gives you the average storage cost. So as far as inventory is concerned, you have 2 main costs kind of draining your pocket here. The cost it takes for you to order new items and the cost it takes for you to store items once they've been ordered. And you end up with that equation. So some things to note here. Notice that because we have this equation, and for inventory cost, this will always be the equation in this class. You can skip step 2 in the optimization steps. Because usually step 2 is to draw a picture, and we draw the picture to come up with the diagram, but we draw the picture to come up with the equation, but in this case, you will always know the equation. You don't need to draw a picture. That's basically it. So the point of, in this question, you're going to know when this is an inventory cost question, because they're going to ask you, with these will be the key words in the problem. You know, you're ordering some items, you know, inventory costs and all that sort of stuff. And basically you want to read the problem, pick out these numbers, right? X is going to be your only variable. Everything here described is going to be a constant. You're assuming that your order cost is fixed, right? It takes a certain amount of money to order. You're selling a certain amount of items per year, per time interval. You know exactly what it's costing you to store them. So this is going to be a constant, this is going to be a constant, that's going to be a constant, X is going to be the only variable here. And so basically now, the point here is to read the problem so you can pick out these numbers. Right? Once you can do that, the rest is pretty straightforward. So, that being said, I only gave one equation here. You return to the hot dog story. Jhevon sells 1,500 hot dogs per year at a steady rate. So I'm back at the hot dog stand and I'm selling 1,500 hot dogs over the course of a year. And I'm selling them at a steady rate. That means I'm under this assumption. It costs $2 to store each hot dog and $10 to order a new shipment of hot dogs. How many times per year should Jhevon order hot dog shipments, and how many hot dogs should be in each shipment? Right? Of course, the goal here is to minimize the amount of cost I'm spending on ordering and storing hot dogs. Okay. So, from this problem, what can we pick up? Do I know what the ordering cost is?
Yeah.
Come again? The order cost is?
$2. $10. $12.
It says here, it's $10 to order a new shipment of hot dogs. Ordering cost is $10. What else do I need? The total number of items over the course of the time interval that we're talking about. So here it's talking about the year, right? Per year, what's the total number of items I expect to pass through my store? 1,500. So per year, I'm expecting to sell 1,500 units. Move on to this guy. Inventory costs, which is basically how much it costs me to store each item. $2. Inventory cost. With that, we kind of have everything. So let X be the number of hot dogs. In each shipment. This means my cost function is going to be given, and it's order cost times total number over X plus inventory cost times X over 2. My order cost is 10 times 1,500 over X plus inventory cost is 2 times X over 2. So this means my cost function is going to be 15,000 over X plus X. So just by knowing this formula, we get here, we automatically next jump into step 4. Right? So step 1 was to read the problem. We read the problem to get this information. I can skip step 2. Jump straight to step 3, which is going to be this formula, something you just memorized and you know at this point. And then now we are back to step 4. Step 4 says we are going to differentiate. Get rid of this. c prime equals 0, so what's going to happen is minus 15 x squared plus 1 equals 0. So do here, divide both sides by x squared, we get minus 15 plus x squared is 0, so x would be square root of 15. Approximation. So x equals, let's simplify that. $150. 25 goes into 150 how many times? 6 times, right? 6 times 25 times 10 times 100. 60, so this is that's approximate size. Okay, so it says what did I want to find? This is 6. How many times per year should he order? How many orders, how many hot dogs in each shipment? So number of hot dogs in each shipment would be equal to that number, whatever that's going to be. And number of orders year would be the total number, 1,500, divided by x, which is going to be 1,500 over
50 square root of 6.
Square root of 60. So boom, 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 boom. It's 30. So number of orders equals around 60. That's the last one. Any questions on this? Optimization is easy. I felt like it went through really quick. I can't tell you. What's easy, what's hard, I don't know anymore. So, as I mentioned, oh, and by the way, I kept remembering to say this, but I didn't say this. Technically, you should be finding absolute max and min. So it's not only that you're testing critical points, technically you're also supposed to be testing endpoints. But the thing is, in all the problems I did, the endpoints didn't really make sense, because one endpoint would be 0, which means the object doesn't exist, and the other endpoint would mean that one side takes the maximum length, which makes the other side 0. So those don't necessarily work. Right, but we're doing the minimum point here. Usually we get only one answer that makes sense and we just run with it. But in general, remember that if you get several, you have to do that first derivative test to figure out which is the one that you want. So as I mentioned, the third test is the Wednesday after we come back from Thanksgiving. So we can all be thankful for that. And test 3 What date is that?
29.
29?
Oh, that's Tuesday. So you mean the 30th?
I think that's the third.
Yeah,
That's the
30th.
30th. So it's November 30th. I think 5 problems. So
5 parts?
5 problems.
Is it going to be?
So definitely you're going to have related rates problem. You're going to have an optimization problem. Curve sketching. Right? That problem's not going to have any parts to it. It's just going to be find all this stuff and sketch the curve.
What about
I will ask you about exponential growth and decay. Absolute maximum. I.e. the closed interval method. Say anything else? Yeah. So exponential growth and decay related rates, max and min values, where we covered relative and absolute max. The curve sketching example is going to test whether you can find local maxes or mins, and then I have to test you whether you know how to find absolute max and min. Related rates and optimization. Yeah, so that's going to be what it's about. Where the bonuses will come from, say, chapter 5.
Chapter.
Okay, yeah. This one's it? I think we do.
Yeah, that's
Let me see my college calendar. Like, I didn't know that.
No, we have class on Wednesday.
for the closed interval method, when it says on an interval and at an interval, what's the difference?
It should be on is the right terminology. So yeah, that's when they give you a function on a b, and then you have to find all the critical points in there, and then test f of a and f of b, and find who's the biggest or the smallest.
So you're not gonna get like over interval.
It'll be the same thing. The interval is going to be important. You test the endpoints, and then you check all critical points inside. Usually the terminology is on the interval. Yes?
The first sketch is gonna be a polynomial.
Yeah, because a
for test 3, it's a polynomial. On the final, I might give you a rational function, but on this one, I will give you a polynomial.
What about for the optimization? Will these be grading? Like the hot
No, it's going to be like the examples.
Okay.
Yep.
Absolute max and min, are there problems in which we don't have critical points? Think of a data power and no critical points that exist.
I don't know, but it's possible. If you test for critical points and they don't exist, then you just plug these two guys in and say, yeah, just use the endpoints. They will be the only ones that matter. Right? And again, it's possible for critical points to exist, but they're not in that interval. You just ignore them. Right? Ignore anything that's not in that interval, basically. So if there are no critical points there, just do these two and see who's the biggest and the smallest. Any other questions?
What about our quizzes? I
What
think we have
quizzes?
2 quizzes left. Maybe.
Okay. So the next topic is kind of a jump. I don't want to start it tonight. I'll let you guys go now. So, see you guys on Wednesday. Next time, integration. Ow!